If you have learned about rates, it's time that you learn about how rates relate to the concentrations of your reactants. So let's take the example of the decomposition of dinitrogen pentoxide, and I'll just write the coefficients and the reactants there. No extra information because we don't need it. And in this equation, if you look at just the reactant side, if you focus just on the reactant side, and you build a graph, like this, and here this axis represents N2O5 and this axis represents time. So what happens is that initially there is some concentration of N2O5 in the reaction vessel, and eventually that just decreases since the reactant gets consumed up. But then as time progresses on, this curve becomes more and more flat. That is because there is no varying change for sufficiently larger times. Now, if you would have plotted, this is a graph, by the way, of N2O5's concentrations versus time. Now, if you would have a graph wherein you had plotted the concentration of N2O5, and that versus the rate of this reaction, if you do something like that, what you can observe is, let's just look at this graph here. So initially the concentration is at a maximum. The concentration of N2O5 is at a maximum. Let's assume that's A naught, or let's just assume that it's C naught, C standing for concentration. And so at C naught, the reaction rate is something like this. It's the slope. We talked about this in the previous video. So here it's A naught for the concentration, and for some large rate, if you plot it, you get this point. You get some point here. And once you have done that, once you have seen the case when the reaction is just in its initial phases, what you can do is you can go to a smaller concentration. So let's say you go to this concentration right here. At this concentration, the reaction rate, it will be the slope of this line. And notice the slope of the white line is lesser than the slope of the blue line right there. So this rate, the blue rate, is, let's just denote it by C1. So rate at C1 is lesser than rate at C2. And that's obvious if you just think about it. If there is a lesser concentration of the reactant, the speed of the reaction will eventually slow down. So then for some other A1, sorry, this was C naught, right? So for other C I don't know, let's just take C1, and there is some other rate, and that rate is smaller than the previous one, so you get another point here. And eventually, if you observe that at the end, if you look at when almost all of N2O5 has been exhausted, so somewhere here, the graph is essentially a horizontal line, and for a horizontal line, the slope of the graph is something like this, and that's near to zero. So as N2O5 decreases, the rate also decreases, and it happens so that this is in fact a straight line. This is in fact a straight line. So it looks something like this. However, it's not true for all the reactions that the rate versus the concentration of the reactant would be a straight line. However, you can simplify almost all reactions to the following. You can say that the rate of your reaction is proportional to the concentration of your reactants to some power. This is some integer, any power, not integer, any power. And for an example of that, so what you could have is, let's say let's take some arbitrary example. Let's take AA plus BB forming CC plus DD. In this reaction, you just look at the reactant side, and what you can immediately see here is the reactants are A and B. So the rate, if you write the rate is proportional for the first reactant. For the first reactant A, you have concentration of A to some power, and that power is not necessarily equal to the stoichiometric coefficient. Don't make that mistake. So this concentration to some power, let's name it M1, and then the concentration B to the power M2, and once you like remove this proportionality sign just means that the rate is equal to some constant times concentration of A to the power M1 times the concentration of B to the power M2. And that's basically what we call as a rate expression. And in this rate expression, this constant is called the rate constant. And we'll build the idea of rate expression, rate constants in the next videos. But for now, let's just focus on the terminology that's involved here. And also, there is something that's called the order of the reaction. So if you take order of this reaction that you have AA plus BB, order of this reaction, there are actually two reactants. Order of this reaction with respect to A, let me just write WRT for with respect to. With respect to A, the order of the reaction is said to be M1, this exponent right here. With respect to B, let me do that in a different color. With respect to B, that's equal to M2, again, the exponent that you have right here. And overall, the order of this equation, order of this reaction, order of reaction of the entire reaction without any with respect to is equal to the sum of the individual orders with respect to different reactants. So in this case, that will be just M1 plus M2. If you however let's take a generic example. Let's take the example wherein let's take rate equals K times A to the power times A to the power 1 times B to the power 2. So in this case, the order of the reaction, let's do that in a bit different colors. So there is one here, A to the power nothing, and B to the power 2. So A to the power 1 would be there. So order of this reaction, whatever reaction that will be, with respect to A is equal to 1. And with respect to B, it's equal to 2. And the overall order of the reaction, the overall order is equal to 1 plus 2, and that's equal to 3. Great. And that's basically the introduction to the rate expression, the rate constant, and the order of the reaction. We can continue talking about these rate expressions and orders. So let's start by taking reactions involving single reactants, And why do I do that? That's just simplifies the problem a bit. So what happens in that case? So basically the reaction is A goes to some products. I don't know what that is. So it could be the decomposition of N2O5. It could be any sort of decomposition reaction you have. It doesn't really matter as long as you're having one single reactant. And now what you can do is you can use the rate. Rate is proportional to A to the power m at a concentration of A to the power m, and you can write the rate expression. So rate equals K times concentration of A to the power m. And in this reaction, this is the rate constant, K is the rate constant, M is the order of the overall reaction, and a rate would just be the rate. If you want to focus on the dimensions, of this K right here, let's focus on the dimension of K. So in the dimension of K, let's just notice a few things here. So the unit for rate is moles per liter per second. So for rate, this is the unit, and for the concentration, the unit is moles per liter. So if you write some sort of dimensional, if you write an equation for the dimensions, so you essentially have moles per liter second equals some constant K times moles per liter to the power M. And so that means that the dimension of K would be moles per liter second times liters per mole to the power M. What I did, I took this entire expression and I spun it on the other side. And that basically gives you the unit of K. And notice if I change M to be 1, 2, it gives you a different dimension. So if M is equal to 1, that is, you have a first order reaction, you have the unit of K to be moles per liter seconds times liters per mole to the power 1. And that's just, you can just cancel out, and that's just second inverse. If you have M to be equal to 0, and those are called zero order reactions, and we will talk about them. But for now, if you want to calculate the dimension of K, that's just mole per liter second times liters per mole to the power 0, and that's just 1. So you just put it out, and that's the unit for K. If you have M equals 2, you can do the same thing. So you have moles per liter second times liter squared over mole squared. Squares get cancelled by the individual numbers, so you have liters per second times moles. And you can always figure out the dimensions just by looking at some sort of a dimensional formula like this. Let's take an example to understand this better. So I have with me acetaldehyde, CH3, CHO. Don't worry if you don't know the formula and things like that. It doesn't really matter. And it decomposes into CH4 plus CO, and all of these are gases, but we don't need to worry about that. And I have the concentrations of CH3CHO and the rate with me. The rate is again in moles per liter second. So let me just write that real quick. So now you have 0.085 for the rate, 0.34 here. If the concentration is 0.2 molars, you have 0.76 if the concentration is 0.3 molars, and similarly you have 1.4 here. Now, if you carefully look at it, you can the problem here being find the order of the reaction. So the problem here is that you write rate to be equal to some constant K times CH3CHO to the power let's take for now M. Okay. And if you do that, if you start by taking that, so let's take any two instances. Let's take I don't know, let's take this place right here and this place right here. So rate 1 is equal to, let's do both of them in different colors. So let's do this in pink. So you have rate 1, the rate 1 is 0.085, and that's equal to K times 0.1 to the power M. And for the one in the yellow, that case, you have the rate is equal to 0.34 equals K times 0.2 to the power M. And you could have used the units here as well, but when solving problems related to the rate expression and the rate constant, the units just cancel out when you divide these equations. So you divide these two, you divide these two. So you would have 0.34 over 0.085 equals k times 0.2 m over k times 0.1 m, and you just divided these equations. Once you do that, you have here the answer comes out to be 4, and that's equal to k's cancel each out, so 0.2 over 0.1 to the power m, and that's just 2 to the power m. So 4 equals 2 to the power m, that gives you m to be equal to 2. And thus you can write this rate not as just m, as 2. So what does that mean? That means if you plot the rate versus the concentration, some rough figure I'll just draw here, it will look like this. It will look like a parabola. So this here, right, is the rate, and this is the concentration of the acetaldehyde you're starting with. So instead of having a straight line, you here have a second order equation, and you get a parabola. And by parabola, it means that the higher the concentration of CH3CHO is, it gives you an even faster rate compared to a straight line. So hopefully that accounts for some introduction to the rate expression, the order of the reaction, and writing rate expressions in general. We have also talked about a problem involving single reactants. We'll continue this discussion in the next video.